everyone, this is Benjamin. Welcome back for a new Zephyr Tech Talk. Is this the 20th? Yeah, that is 20th episode. We've been doing this for a bit over a year. So I guess we've been pretty active. It's good to be back. There was a small, a couple of weeks of hiatus because I was away. We had to cancel basically today's topic. Should have happened a couple of weeks back. But we're back to talk about all things Bluetooth, simulation of all things wireless communications, and a bit of code spaces and coding and using Zephyr in dev containers. So it should be pretty fun. While we gather folks, whether you're watching us on YouTube, on LinkedIn, take a moment to just say hi in the chat. If you don't mind, it's always nice to see where people are joining us from. I'm joining from France today. So let's see who else we have. If you're watching on YouTube or on LinkedIn, don't forget to subscribe. That's also a good way to stay in touch with the community. There's going to be, speaking of YouTube specifically, we're just, I guess, a day away from Zephyr 4.0 release. And I'm hoping to publish, as always, a video that will try and cover some of the new features and additions. So should be, watch out for that and subscribe so that you don't miss it. And we have Bluetooth people joining us. We have Johan, we have Karthik from, we're missing the country, but Tyler from Denmark, Marcio from Brazil. All right, I'm going to take a pause. Hey, from India. There you go. Take a pause and bring our speakers, and then I'll go through all the comments again. Our guests and speakers for today are Jonathan and Alberto from Zephyr / BabbleSim / all things Bluetooth. I'll let introduce themselves so that they can tell us a bit more, and then we will dive into today's topic. As always, you don't have questions just yet, but make sure that you use the opportunity of this being a live exercise and a live show to send all the questions you have. Let's start with Jonathan. Who are you?
Hey, I'm Jonathan. Worked at Nordic Semi for the past 4 years on the Bluetooth host recently. And I've been using BabbleSim and enjoying it for the last 2 years.
Cool. Alberto?
So I also work in Nordic Semiconductor from Denmark, and I'm maintaining in Zephyr the native targets and also BabbleSim. It's something that we implemented quite a few years ago in my previous company, so I'm happy to talk about it today.
Yeah. So let's get started. When I reached out to both of you, I was like, okay, in the Zephyr ecosystem, I see this thing called BabbleSim that seems to be pretty neat. I myself don't have an immediate application for it, but it feels like it's something really, really powerful, really mature. There's lots of documentation, etc. But I wouldn't know where to start, and I'm sure there's lots of like hidden gems in it that I don't know about. So I'm sure others are probably in the same situation than myself. So let's have a chat and let's just record it and stream it, right? And so why don't you and maybe Alberto, you can start. Why don't you tell us a bit about what it is? What's maybe also the history? I realize I don't even know. Like, are you the author, inventor of BabbleSim?
Yeah.
Okay.
Yeah. So BabbleSim was born quite a few years ago, actually, and it was born out of a really strong need that became very apparent when in my previous company we were developing Bluetooth low energy devices. I mean, when you are developing, network devices, it very fast you find yourself in a situation where some issues can be quite challenging to reproduce. Like, you have a bug that may depend on, they will always depend on what other devices are doing, no? And they may depend on packet loss, they may depend on interference, they may depend on, who booted too late or too early.
And if you put a breakpoint in your application, then basically the radio stack might just stop. So
yes, you will time out, and that's it. So indeed, the debugging is, a very, very challenging challenge. Let's put it this way. Another thing that we also, that is quite, typical when you're developing network devices, that, well, of course, you want to test them, not only to debug issues. And if you want to properly test, like integration test your code, you will end up with, having several boards on your desk and, try to run your test there. But of course, you cannot scale that too easily. No, for scaling it, you start needing shielded boxes where you put your, your boards, and so they can communicate there. And then you need, a PC next to them to flash them and, start the test and, read the results and so forth. And then if you have, tens of developers working in your project and you want to run, a few hundred tests for each PR or for each, or in the nightly runs or so, suddenly you don't need, just a couple of setups. You need a lab full of setups, and you need a team for maintaining these setups. And it really scales horribly, let's say, from, you have this trade-off of cost versus time versus how much you want to test, and you always end up testing way too little or much less than you would like to test. No? So that was the drive to build BabbleSim. It was, wanting to be able to test our software and debug our software just in a computer without the need to have actual hardware, so that we could do it faster and cheaply. So how this was done is that, we have the radio, all of it simulated in one process. That is what we call the physical layer simulation or the radio simulation. And this process, this program, is running in your computer. You start it when you want to run your simulation, and then you have each of your devices compiled as an executable for your computer, and then that device can talk with the radio simulation. So if you have 10 devices in your simulation, you have 10 executables, each of them talking with the radio simulation. And this radio simulation is responsible to handle all the radio itself, the simulation of the radio, the interference, and ensuring that what is received by somebody is what should be received. And it's also handling the coordination in time of devices. So if one of the devices stops in a breakpoint, your whole simulation stops. Doesn't stop, it stalls, it pauses there. And that if, some of the devices is running slower for whatever reason, the whole simulation actually runs slowly, so that you can actually, instrument your code or do whatever you want. So that was the need and the drive. So maybe I can talk a little bit now about how you can actually get started in Zephyr, how you can, where you can find information about BabbleSim and so forth. So if you just want to find information in general about BabbleSim, you can go to the babblesim.github.io page, and here you can find, a bit of general information. But if you are a Zephyr user, and I expect that most of the people listening will be, you actually have a quite fast path, so you can skip a lot of reading. You can just go to the documentation for the NRF 52 simulated board. And here actually you have the exact steps you can do if you just want to, get the BabbleSim built in your computer and running. So you have here, just in your Zephyr workspace, you enable the BabbleSim group of repositories. So you get the source of BabbleSim just by doing west update. Then you go to the...
Is BabbleSim cross-platform, or would that be Linux only?
Linux only.
Okay.
So yes, you need a PC running Linux. And then you go to the folder where all the sources have been fetched. This is where they go by default, and you just make it. And now you have it built. And then the only thing that you also need to do is to say, to set these two environment variables, which I recommend setting in ZephyrRC, so that you know where the simulator is. And this is because you don't need to fetch it this way. There is lots of ways to fetch it and places to put it. And once you have done that, you just build exactly like you would build any other target. You only need to do that once, and you are ready to build. And of course, when you build, you are not building exactly like you would build when you are building for a normal target. For a normal target, you would build an image that then you would flash, and then you would reset your device and run it. No? When you are building for BabbleSim, what you are really doing is building your embedded software, meaning your application, your Zephyr kernel, the Bluetooth stack or 15.4 stack or whichever, the real drivers, like the real drivers for the Nordic hardware, just like for this NRF52. You are building all of this together with the native simulator and together with the models of the Nordic NRF hardware, whichever variant you are choosing. If you choose the NRF52, you are actually building with models of a 52833. And all this together is built as one executable for your Linux computer. So actually your code is built for x86. Your code is not, interpreted in any way. This is not QEMU-like. Your code is really built for your host. It's just that when your code tries to, interact with the hardware, it's actually interacting with the hardware models instead of with real hardware. And then what happens is that the hardware models, whenever there is radioactivity, they will, send that radioactivity to the physical layer simulation. So you will be able to, send or receive packets around. So I can show you in practice a very simple example of how this works. So I have here, as I said, you can just build with West or whichever normal way. If I just build here, with the Mecha Ninja, and here I'm just building, Hello World, I'm just building it like you would build any other application. And the result is an executable, as you can see here, in the Zephyr folder. And I can just run this executable like I would run any other Linux executable. Now I just press Ctrl+C to stop it. And you can see that what normally would have come through the UART or whatever else you are using to get your logging output from your device out, in this case, it's just coming directly to a standard out. You can also see that the executable is warning you that you are not connecting to a physical layer simulation. And that's just because you haven't told it how to. So it's assuming you don't want to do that. The executable actually takes quite many parameters. I just run it with ---- help, and you can see that there is lots of options. You can say if you want to have the flash in a file, or if you want to, connect the UART in loopback, or if you want to, connect GPIOs and so forth. You have lots of options, and what options you have depends on what device you're building and what peripherals that device has. So maybe I should show now an example that would be a little bit more entertaining, because Hello World is really boring. I can just show you.
And I should have mentioned, or I thought about it before, but Christopher in the chat is saying that obviously BabbleSim also works in WSL too, so you can just use Windows for those.
Yes, that's very right. Thank you for that. We don't need to scare people away if they're using Windows. Yes. Okay. So here I will then build just one of the samples. I will sample the peripheral hard write monitor sample. This is just so we can have some kind of traffic. And here I will build the central, the equivalent central. And now that I have built both, I can just run them like before. But now what I'm going to do is actually give it some parameters so they can actually connect to the physical layer simulation. So if I, here what I'm giving is, the first parameter is this -s, is the simulation ID, which I'm just calling it hola, which is hello in Spanish. And this is just a string that will identify uniquely the simulation. Just any string that is unique. And I'm also telling to this executable that this is going to be the device 0 in the simulation. So now I have started executing it, and it's just waiting. It's waiting for the physical layer simulation. Similarly here, I'm going to start the central device. This was the peripheral. This is the central. I'm going to start it with the same simulation ID. So they connect to the same simulation. And I'm going to tell it that is device 1. Now this device is also waiting for the physical layer simulation. And now here, I'm going to start the physical layer simulation itself. I give it the same simulation ID. I tell it that there is going to be 2 devices connecting, because if there was more, it will actually wait for them and it will not let the simulation go until they have connected. And I'm telling it, okay, run for 10 seconds. And as soon as I start the physical layer simulation, everything has run to completion. So it's really as simple as that to run a simulation. Normally you will, have this in a shell script or so, where you just have all your tests. But here I'm just running them in 3 terminals so that you can see how easy it is to run. Now, as you saw, when I ran things started as soon as I started the physical layer simulation, but I could have actually started things in another order and I would have got the same result. The physical layer simulation ensures that things run only when they can run. And everything is built in a way that if you run it 20 times, you get 20 times the same result. I mean, if you run the same thing, of course. That is, everything is reproducible and any randomness is really pseudo randomness. So if you want to have, a different result, you would need to provide either the device or the physical layer a different random seed. So you have, a different simulation, let's say. That, of course, makes it much easier to debug and to, go around your code seeing what is happening. So another thing that may be actually very interesting for people is that, all the, okay, I will take this out, all the traffic from the simulation, all the radio traffic is actually being dumped to disk. And that can be quite easily converted. I'm sorry that this is very small, but I don't think I can zoom it in because this is just this tool. Can be converted easily into a trace. I mean, there's a script to convert it into a trace for the Elysis Bluetooth analyzer software. And here I have just imported the trace that I have just run. So just like you can, trace from there, with a real box from this, from Elysis, you can get the trace here and you can see the packets just like in real life. So this can be quite useful if you want to, debug what is happening in your connection.
And Wireshark has some level of support for Bluetooth,
Correct.
does it not?
Yes.
Would
Yes.
that work? Would that be an option?
Yes, we also have a script to convert the traces into Wireshark pickup or pickup NG traces, and you can also import those. It's just that the Elysis tends to be more comfortable. I mean, it's a bit more advanced, but you certainly can use Wireshark if you want.
Nice.
Yes. So yes, so what you are, getting here, I mean, is effectively what we were hoping at the beginning. I mean, you get reproducible tests, as you saw. You get things running much faster than real time. Of course, it depends on how fast your computer is. It depends, how many devices you're running and the load and so forth. But you can see that it's in the order of 100 times faster than real time. You can run any device or all devices in a debugger and things will just work as before. Like running a debugger will not have any effect on the simulation. You can also run with instrumentation, meaning you can run any of the devices in Valgrind. You can build them with the address sanitizer if you want. You can build them with the undefined behavior sanitizer. I mean, it is as simple, as setting the option. So you can just say config ASAN equals yes, and now you are building with the address sanitizer. And if you run this, it will run with the address sanitizer. In the background, you will not realize from the simulation only if the other sanitizer finds something, you will get a printout. You can also run with coverage if you want, and then you have the coverage stamp with coverage enabled, so you get the coverage file stamp, and then you can collect them with JCOB or LCOB. And all that you actually need is a Linux computer or BSL2, which means that it's really quite nice for for your local development or for CI, because the thing is, all this can be scripted, and then you can just have your tests as we do in the Zephyr CI being run there for each pull request or nightly or so. Yeah.
Nice. So I don't see any questions yet in the chat, but I sure have many. One is actually, wait, this doesn't look really good. Let's do it this way. Does it make sense, or is it possible to have scenarios like where it's a mix of a simulation and real world devices?
Not exactly. So the thing is, in simulation, everything is in the simulation. No? So as you saw, also time is much faster than real time and so forth. We do have there is a funny device that is called the handbrake, that if you connect it to a simulation, it will actually slow down the simulation. And that is meant to allow you to have some real-time interactions. So if you, for example, have one of your devices, you want to interact through the cell with it or so. So there is some means to kind of, come out of the simulation into the real world. But we cannot have, we don't have any means of, sending traffic from the simulation out or getting traffic, real Bluetooth traffic into the simulation. We can run without BabbleSim, just with the native simulator, the Bluetooth stack using the Linux host.
Yes.
So you can use, or use an attached Bluetooth controller, but that is, fully decoupled, let's say, from this BabbleSim simulation. It's a bit of a different, environment, let's say.
Yeah, makes sense. A question from Masha, but maybe this will come later in the flow of the presentation. But if not, then maybe we can cover it now. In terms of actually writing tests that check the behavior and the functionality of a Bluetooth application, can you shed some light on how one could use potentially Z-test or Twister, I guess, to test the behavior of their Bluetooth applications?
Of course.
And maybe this is what Jonathan will be covering as part of the demo, so it's also fine to transition to that if that's the case.
Well, so with regards to Z-test, we do actually have quite many tests in Zephyr that are actually running in simulation, but they are running, the tests that are Z-tests are running in one device alone. No? So Z-test is like meant for, or kind of, is like, you flash your device, your test runs, and then your test reports pass or failed. So we do have quite many tests where we're running in these simulated targets, but we don't run Bluetooth connectivity on those tests. So Z-test is fully supported in the simulated targets, let's put it this way, but we don't have any further support in Z-test for simulations with multiple devices. Similarly, Twister is not multiple device aware, let's put it this way. So Twister works in a way that, it builds, today, it builds one image, it flashes that image, or in the case of the native simulator targets, it runs that executable, and then it looks at the output, but it runs, one thing at a time. It's not aware.
But for example, if I'm not mistaken, things like the tests for the lightweight M2M client, as part of the tests, it boots up a Docker container that would be the server. So similarly, one could think of the Twister test as something that would, before starting, would put together, fire up an existing simulation so that the device under test would be joining that particular network, maybe.
Yeah, so that is certainly possible. And I don't think we have as a Twister test today, a test like that, but we actually have an ongoing task that has quite a bit of attention to be able to have Twister be more aware of having, because the thing is, one thing is I want to build one image that I run then with some external program. Another thing is I want to build 5 Zephyr images, let's say, and run them with the external program. No? And that's where we have this task of, okay, we know that this and this and this and this test need to all be built and then run together. So there is this kind of dependency of what you need to have built before, and then you can run them all together in one test, and then you can collect the result. So that's something that we very much want and we want to enable. So that's something that we hope we will have in Twister relatively soon. Okay. For this kind of network devices, we have our own separate set of shell scripts where we just, in there we run the tests, so we can, just build all the images we need and then just run them all together, and they can just interact.
Yeah, makes sense. Quick question from Tyler. Quick, maybe not. How about simulating behavior that involves hardware variances like crystal tolerances, bad antenna matching, all things, radio interferences and whatnot?
So that's a very good question. So today in the Nordic models that you can just get, there is a crystal drift, but it's a very simple crystal drift. Actually, it is certainly possible to have much more accurate crystal models, and I have done that before for actually BabbleSim simulations, but there is no open source models for that. But it is certainly possible. With regards to antenna matching, there is no simulation of that today, but again, it could be done. That actually kind of hints me that maybe I should show something that people could be interested. And so let me see very fast, bear with me. So, okay, so I have just run this simulation here, and you guys, of course, may wonder in this connection what has happened, how is it that things have connected? And the thing is, by default, the physical layer is running with, the default way it connects things physically, let's put it this way, is like if you had a cable and a RF splitter of 60 dBs. That's the default. And it's the default because it's very simple, let's say, and it will just get you running for a lot of software testing, simply. But you don't need to run with that very simple default. You can actually select, and this is just from the documentation of BabbleSim, other models of the channel and other models of the modem itself, or of the different devices modems. And for the selecting the channel, you just effectively pass the channel option, and one channel that you may want to select is the indoor channel model. And then this channel gets some parameters. It gets much more parameters than this, but this is just an example. And for example, what this channel model does is that it provides you a realistic realization, statistically realistic realization of the channel indoors in the 2.4 gigahertz band. So what you get is just like here, this figure is showing, one realization from that channel model of the fast fading, so the multipath effects. And you can select different, presets, or you can actually go and tune individual parameters, and you can get, different realizations depending on the the delay spread and depending on the speed, or at which somebody is walking, the device is walking, and so forth. So there is actually quite many choices there. So this channel models the fast fading effects, meaning multipath. It models also the path loss, meaning distances between devices. Devices can actually move around and they can, get closer or farther. It models inter-symbol interference effects. So you can actually use this if you want, but you need to choose it. By default, you don't have this because it's a bit of, a quite much more complex situation that many people does not need. This is more of a, system level simulation kind of thing. You can also select a different modem model. By default, you have as modem model this, that is the magic modem model. And it's called magic because it's more than ideal, let's put it this way. It's completely unrealistic, but it just gets packaged through, let's say. So you don't need to actually worry about power levels and so forth. All that you need to, this will get a packet through if it is just the receiver is open at the right time in the right frequency, let's put it this way. But you can also select the BLE simple modem model. And this other model is a model that is this one. You have here the documentation. You can find it in here. If you just search for the this simple model is here. The idea of BabbleSim, by the way, is that it's a sort of plugin based tool. So you can just fetch repositories with extra devices and you can just, build them and run them. So the simple BLE model is a BLE model is effectively a sort of simplistic generic modem model. It's not any particular model or any particular modem, but it includes the kind of effects that you would hope to if you wanted a relatively good but simplistic simulation. So you have the effects like co-channel interference or adjacent channel interference. You also have the effects of the modulator, of the thermal noise, of course. And if you just use the default parameters, you get a sort of generic goodies radio performance, BLE radio performance. And this, for example, is the 1 megabit performance for, with the default parameters, so the bit error rate versus power in the antenna with no interference and so forth. So this is also an option that as a user you can choose. You can also choose to run with interferers. So of course here I just ran before with just the central and the peripheral devices, and that's it. But you can actually run if you wanted with, for example, this device. This call here is just everything that connects to the physical layer is called a device. That is this VLAN activity model that will actually behave or produce interference like a VLAN would produce. So with this device, you can pass it several parameters, and you can say like, okay, generate interference like if there was a video stream going in the VLAN, like somebody was watching a movie in their TV and that was going over the VLAN, or like if the VLAN was completely saturated with traffic, or like if somebody was downloading a massive file. So you can run this device also in your simulation, and you will have the interference being transmitted and your device is being affected by it. You also have, if you want, a way simpler interferer, that is this burst interferer. This is more like if you know what you want to jam, you can just run this guy. So to this guy, you can say, okay, I want to transmit interference in this frequency range, in this time range of this type of modulation of this power, and I will just jam you in those frequencies and times as you tell it to do. So you have options like this to actually run simulations that are more interesting, let's put it this way, or where you actually can see some other effects.
Yeah, so that's exactly like I said in the intro. I knew there were probably tons of really cool stuff within BabbleSim, and I had no idea what it was. You just showed it, so that's that's really cool, and I think that answers hopefully Tyler's question. We have quite a few more questions around BabbleSim specifically, the capabilities and whatnot. We will save them for later so that we can move on to sort of like not the second topic, but basically extending on why it's actually interesting to have good simulation tools. One is it helps you actually test your functionality without having the hardware, but it also helps quite a lot when it comes to the developer experience. When you want to say you're like a Zephyr user, you work on a new feature, whatever, you want to quickly hack something together. You're not even on your dev machine, you're on a plane, whatever. There are tools now that allow to run basically everything in the browser. So we are gonna bring Jonathan on stage to tell us a bit more about what you've been working on recently. I think there's even a pull request that hopefully will make it into Zephyr really soon. But I would love to see how. I'm guessing that you're starting to use this more and more yourself, in your own workflow. So what does it mean to basically develop Zephyr and use Zephyr in the browser?
It's nice because you don't have to care about the toolchain.
Which is there's a lot, right, that you need to install when you want to hack Zephyr. Like there's the Zephyr code, that's one, but then there's all the HALs and all the tool chains, which it's convenient to have already. We take care of providing the tool chains to the users, but then you still need to install them and to download them, and that's gigs and gigs of space. But would love to see. That's something that for the past couple of years I've been trying myself, and as you know, and as some of the people watching us know, you will find in tons of GitHub repos or gists or blog posts of people who, one way or the other, have been trying to set up dev containers for Zephyr. What you've been doing, I think, is getting really, really close to what something that we could actually get to the point where it's available upstream for everyone to use. So I guess you will show us a demo, and we will get lots of people saying, "Yay, it's really cool!" And this will give everyone an incentive to finally, make it available to more people. So you have what, like, let's say a sample, some application that you've been putting together.
Yeah, so here I have a sample repository set up.
Can you zoom just a little bit?
Can I zoom? Yes. Better?
Yeah, maybe a bit more.
A bit more? There you go.
Yeah, that's good.
All right. Yeah, so this is a repo that shows how to use BabbleSim as a developer and how to use the dev containers and GitHub's hosted version that's called code spaces. Yeah, this thing. So this is a try it at home stream. So you can go to this
Yeah, I was
URL.
gonna
I
say,
don't know
like,
if
I'm
you can
gonna
paste
put
it.
the link on screen. I mean, it's on screen already, but make it. Whoops, that's not that. Where am I? Whoops. There we go.
There we go. Yeah, so if you go there, you log in with GitHub, then you can click on code, then on code spaces, this thing, and create a code space. And here I've already done this, so I won't do it again. But then it will basically set up the whole environment with the tool chain, and it will download Zephyr, do everything in order to let you develop.
Basically, based on whatever is in the dev container folder, that's basically where it says like what kind of like which version of Ubuntu, whatever.
Yes. So the dev container thingy has a configuration file where you can set up the extensions you want to have and any VS Code settings basically, and then you have some special commands for initialization when you spawn the container and when you update the contents of the repo. And then it uses an image, which is a Docker image, and you can define it with a Docker file, or it can be an image hosted on any Docker repo.
Yeah, which in your case, like the image it's already been built, right? Like when you open the container, it fetches it from the GitHub container repo, right? Yeah.
Yeah, I did a pre-build and I uploaded it.
Okay.
Yes. Yeah, and then you can define some scripts. Here, for example, setup env will do a west init. So the stuff you usually, this is basically the getting started page for Zephyr packaged into a single click. So you have a west init, west update, and this will use the west file that we set up here that has only what we need for BSIM development, which is the BSIM group, all the repos that Alberto just showed, the HAL for Nordic, because we're running the NR52 models, and the models themselves, and some crypto stuff too. All right, maybe I should get into it. So if we go into the dev container, we're dropped into a VS Code instance. Starting up.
So in your case, it was just it was idle, right? It won't rebuild it from scratch, or will
it's pausing it.
Yeah.
So I didn't mention it, but you can definitely run this locally. You don't have to go full cloud with this. If you have VS Codes, you can, in the README, it says here how you can do it. You install dev container extension, and then you open the repo with VS Code, and there's a pop-up that appears, and then the rest I will show.
Yeah, plus, and we were discussing that before going live, there's only so much that one can do with the free tier. Like I think GitHub gives you probably like a couple dozen hours of code spaces compute time. But then if you want to do more, then either you pay or you use the same paradigm, like you just said, and you just run the containers locally, which still gives you a great experience in that your dev environment is 100% reproducible. So that's
and contained, not all over your machine.
Yep.
Which is nice. All right, so in this demo, I will be reading. in this demo, we have a developer trying to build a central device. So in Bluetooth, it means a device that will scan and connect to another device. Here, a peripheral. So for example, it could be a bicycle computer connecting to a heart rate sensor for displaying the heart rate on the display. And what we want to do is connect to the heart rate sensor, figure out where in the, there's a table in Bluetooth called the GAT, and there we have all the services, and the heart rate measurement is one of them. So we have to find out where it is in that table, and then subscribe to the notifications, it's called. So whenever the heart rate value changes, it will send a packet back to us. We have to enable that. So we'll try to run the application and see what happens. So it's under GAT bug, under central, source, may not see. Then we enable Bluetooth and then start, and then the rest is all chained through callbacks. When we found a device, we connect to it. When we have connected, we start discovering the services, and once we're done discovering, then we subscribe, and we're supposed to get measurements out. So let's try to run it. We do file, or run rather, and then start debugging. So here it will build the two applications, the central and the peripheral, and then pipe them together with the physical layer simulator, like Alberto showed, and then attach a debugger to the central and finally start it. So now it's started, and it's running, and we can see the output in the file here. So we see that we have started, so finalized. Yeah, we're device 0, so this is us, rather. And we can see that we're connected. We found some attributes, so those are entries in the GAT table. So we found some of them, and then we're done discovering, but we have no data. There's nothing else coming out. So that's not nice. So we have to figure out what's happening. So I will stop the debugger. I'll show something really cool. Once I've stopped the debugging, we can click on the trace.pcap. Someone asked about Wireshark. Look at this. Isn't this nice? So you basically have a Wireshark in the browser. And I will just filter out the packets we don't care about. So with length equals 0. All right, maybe I have to de-zoom a bit. So we see the packets exchanged, and we see, get this out too. And we see that we have the discovery packets. So here we're looking for the service, heart rate service, and we get a response. Let's maybe expand this. Yeah, so it did find a heart rate service, and then we're looking for the characteristics of that service. You can have multiple sub kind of values. And we get a response to. That's nice. We got 2 of them. One is the heart rate measurement. The other is the body sensor location. I think we're interested into the heart rate measurement one. So it starts at 1B, ends at 1C. And then we send another request starting at 1D. And so how the attributes are organized in the table is you have the definition of the characteristic, and then you have the value mostly, and the next one is the place where you want to actually subscribe to the notifications. So that's what we're looking for right now. Yeah, so we're asking for that, and we're getting a Wait a minute. No, not there. So there we were asking for the details basically, and here we have the values. Here we have the value, and now we're actually asking for where to subscribe. But we're not getting anything. We get an attribute not found. So maybe we should look at what type of characteristic we ask for. And here was asking for a declaration. This doesn't look right. We should be asking for a, I think it's descriptor.
Right.
This is very Bluetooth. It's very, I'm sorry about that. It's just to show how nice BabbleSim is to use. So we know that something is wrong and we have a bad type when we send that packet. Now we have to figure out where we send that and what logic leads to us sending that bad packet. So we go back to our app and we go to the discovery function, place a breakpoint, run simulation again. Yeah, so the simulation has run and we're already paused at the right place. So this is nice. We expect it to be called 3 times, I think. Once for this thing, another for this one, another for the last one, where we actually do the subscribe call. So we expect to be called there. Hit run. Yeah, get there, run again, and then nothing. Okay, let's try it again. I think this works. Let's try it. Yeah, so we run the first time and we see that we step into there. Good. Let's go to the second call. This time we execute this other one. And here we're supposed to set the right type. And we see that the type is of the discovery params is missing for some reason. Here we set it. We forgot to set it here, probably. And we can inspect all variables and stuff. And you saw that I hit play on the real device. I would have crashed already. And then I would have had to wait, I don't know, 3 seconds to reconnect, start discovery. And so it's much, much, much faster than with a real device. Yeah, you can step into whatever you do with the debugger. All right, so we know that we're missing a type. So let's stop here. Copy this. And then let's discover a descriptor instead. That's what we want. The downsides of working in the browser, the shortcuts don't work like you expect them to. Yeah, I don't know if Control S works. Let's try that. Yeah, maybe. Let's debug again. Run, start debugging. So once, twice, thrice. That's better. And we actually go into the subscribe branch. That's nice. Let's let it run for a few seconds. And we can go inspect the output. Look at that. We have managed to subscribe, and then we get the data, and it's still spinning. And as last time, we can inspect also the actual packets. And we see if I add the filter again. Yeah, we see all the notifications here with the value of the heart rate sensor. Success. We have debugged an app with BabbleSim. Yeah, so this is at Nordic, we did this a lot. We had So I was part of the team that maintained parts of the host, and we usually had bug reports like, if I connect and disconnect like 30 times in a very bad environment, then the host crashes. This kind of thing is super tiresome to reproduce, because then you have to spend 10 minutes trying to make a crash, and then you can step one time, and then the device crashes in the debugger. Not nice. So the first thing we usually did was make a test with BabbleSim, and then we're able to run as many times as we want, and it's fully reproducible. Yeah. It was very, very useful. I can show here a test, a sample test that we have. So there's some documentation now on how to write tests with BabbleSim and Zephyr. And yeah, it looks like this. So you have, yeah, you run stuff and then you assert, like, it looks like Z-test basically, but it's not Z-test. Yeah. Next demo. If you have, do you have any questions? Yeah, sorry.
Well, I was wondering, given that we are already sort of in the GitHub ecosystem, I did an experiment in your code space, though, to ask Copilot to find the bug, and it kind of did. So that wasn't. That bug is mostly a typo, I guess one could say. So this is a good exercise for LLMs and AIs. But yeah, it was really, really impressive, and also nice to see that extensions such as the one you showed for the PCAP also work just fine in the browser. So that's pretty cool.
Yes, yeah. Yeah, I think VS Code is kind of the new king of IDs, whether we like it or not. And if we can leverage that ecosystem, that's pretty nice. I have another demo, and that kind of maybe answers the question.
Tooth stuff and BabbleSim, etc. But the container itself and the extensions it pulls by default, etc. Like that's something that's applicable for any Zephyr development, and the fact that it already has the debugger pre-wired, etc. That's really, really convenient. So there were, I hope there will be some questions on that part of the demo in particular, but catching up on the and I will bring Alberto back on screen. I mean, we saw that again as part of this demo, the hardware simulation. Oops, sorry, that's not the one I wanted to bring up. This one first. In terms of simulating actual hardware, is there only Nordic NRF simulations available today, and or is it possible to create your own?
It is possible, but then you need to create it, of course. So open source, today there is only Nordic hardware models. You actually don't even need to have hardware models if you don't want, depending on what you want to do. So the API to the physical layer is standard. Let's say, I mean, standard is stable and relatively simple. So you can actually interact with it through, from Python scripts. You can interact from it to it through whatever from whatever you want. You just need to, fulfill that API contract to be able to send and receive. You can then implement.
You don't need the modem part. Like you don't need to.
Correct. Yes, and you don't need to have the hardware. Let's say that you don't need to write 2 registers from your software and something that then pretends to be behind those registers. But of course, if you are writing embedded software, you may want to have something that pretends to be your hardware, and that's why we have the models of the Nordic hardware, so you can run the unmodified or as unmodified as possible software and test your software. But yeah, you can certainly write your own, and there certainly is other models out there. But just if other companies want to make their own models open source, they can do them, and that's it.
Cool. In terms of simulation, is there a way, and is there a model for simulating power usage?
No, unfortunately, that is not today. So it could be actually done, but we don't have that. I mean, we could, have our models generate, information about how much they are running, for how long different peripherals are running and stuff like that, and then try to guess from their power. We do not have, though, any kind of good way today of simulating how long the CPU is running, because we are running, not only we're running in x86, but we're running in the native simulator-like environment. So the CPU runs infinitely fast, let's say, compared with the hardware. So we don't have actually anything like that today. But at least for the hardware side of things, we could get some understanding. And if you wanted to, it would be quite easy to get some understanding of how much power you're using in, transmitting and receiving.
It's basically tracing on steroids, like based on how many calls you're making to this and that, you can sort of guess.
Yes.
Yeah.
Yeah, exactly.
Okay. Muhammad is asking whether it's possible to simulate 15.4 traffic.
It is, and we do have actually a few tests upstream testing the 15.4 stack and testing actually OpenThread also. So it is possible and it is running.
Cool. I like those short answers. Mauricio was asking, are interrupts simulated?
Aha. So interrupts are simulated by having the hardware models call a function in the interrupt controller model. So effectively, it's like if a signal is a function call. No? And then what happens is that the interrupt controller model will, if the interrupt is a mask, awake the CPU, and the CPU will, the CPU. So there's a model of the CPU, if you wish, and the CPU model, it will start executing the interrupt handler. And when I say CPU model, it's not like we have an actual CPU model. We just, have something that can sleep and continue executing code and can, run the interrupt handler and so forth. That's the level of CPU model, and there is no instructions and stuff like that. So an interrupt effectively is something that, wakes the CPU if it needs to be woken, runs the interrupt handler, and then, the context switch of the OS can take it from there, of Zephyr, of course.
Okay, cool. And with that, I think we caught up on questions. We are pretty much right on time. That was really good. I hope, if people missed it, they will certainly catch up on the recording. There were tons of interesting pointers. The link to Jonathan's GitHub repo is there. We can probably also put the link to the pull request to add the dev container definition to Zephyr. I will put that in the comments on YouTube and on LinkedIn. Again, if you're not subscribed to the YouTube channel, to LinkedIn, consider doing so. Put some likes, etc. And it certainly helps with spreading the good word about Zephyr and its ecosystem. We will be back next week. We were away for a couple months, but now Zephyr 4.0, like I mentioned, is just around the corner. So we will be spending some time with the release managers and some of the maintainers to talk about what's new. So next Wednesday, same time, basically. If you would like to be to join me on the show, if you have cool topics, whether it's Zephyr, like 100% Zephyr, or just cool embedded stuff in general, just ping me. I would be happy to chat with you on what could be a good topic and potentially have you on the show. And yeah, with that, I think it's a wrap. Mauricio is happy. Oh, there's actually I didn't see the second part. I put the stuff on screen. I was like, thanks, Mauricio, for being thankful. We might need to take the questions offline. Like, please put them as well. Okay, let's take this one, and then if there's more, we will be taking them offline on LinkedIn as comments. Is it possible to simulate devices that have multiple CPUs accessing the same peripherals?
Yes, and for example, the 5340, simulated 5340 from Nordic has two MCUs. So yes, it is possible.
Okay, so that was a short answer, Mauricio. If you have more questions, well, I think you're actually coming from YouTube. Just drop them as comment on YouTube, and we will make sure to have Alberto or Jonathan answer them there. And yeah, with that, thanks again, Jonathan, Alberto. We did it this time, finally, and we will be back in next week. I guess. Thanks, everyone. Bye.
Thank you. Bye.
Thank you. Bye.